All right, welcome Jonathan Klonowski for his talk on accelerating the U.S. bioeconomy. Excited to hear this. Jonathan, take it away.
Yeah, definitely. And this might be a little scuffed. Uh, Lots of things happening recently. But hi, I'm Jonathan Klonowski. I'm with EBRC. EBRC is a public-private dedicated to advancing the bioeconomy. We work on things like road mapping. How does engineering biology plug into different national priorities? Policy and international engagement, trying to get government to support and yeah, trying to get government to support and trying to get international collaboration around engineering biology, um, and also security, so biosecurity, yeah, preventing biotechnologies to be to be misused, and education, trying to educate the next iteration of scientists in engineering biology. But today, I'll be talking to you about accelerating the US bioeconomy, overcoming ecosystems barriers to advance laboratory automation. I'll actually be talking a little bit more broadly about this project. It is kind of a weird spawn baby of this kind of this first part, which is kind of more uh, workforce academic, a little bit informing kind of the workforce kind of policymaker, the kind of economics person. The second part, which is kind of like informing the not yet automated lab on like what they might need to know like before like going in, yeah, going in on automation. And finally, part three is kind of the big one I'm gonna try and talk to you guys about, and that is like what can OSTP, or what can like government, and OSTP is the Office of Science and Technology Policy, do alongside the ecosystem to try and kind of overcome barriers and get things going. But I don't expect to tell anyone anything new here. I'm just trying to kind of highlight things that I've yeah, highlight that same things that I have said or to other people. And so what I'm looking here is like, am I missing anything? Did I misunderstand anything? Are the priorities like kind of off? Should I be prioritizing something else? But yeah, so that is I'll start there. Kind of a long lead in. Um, okay. So what is advanced automation? So I'm kind of defining it as systems integrating physical and digital tools to not autonomously execute complex processes. And so I kind of made a little baby figure where you have physical automation as some sort of like fixed automation, can be something as easy, as PCR or a pipette. That's like the most basic. Then we have programmable, something that's a little bit more flexible, like a liquid handler, and then flexible, which is like a robotic arm. It can basically do anything. Then on the cognitive side, we have like explainable algorithms, if-then decision trees. More complicated is statistical models and simulations. And finally, we have our modern computational methods like machine learning. And so advanced automation combines physical wet lab tasks with computational methods, automating information and task-based database tasks using a combination of moderately complex methods. So I'm basically saying the cutoff for advanced automation is you have to be using something a little bit more complex than fixed automation, and just fixed automation and explainable algorithms. And so my research question is going into this is, what is the state of adoption of advanced automation in the biotech industry, and what have been the organizational and workforce impacts of advanced automation? Um, and so what makes this time different? Like why is automation kind of coming to the forefront again? Because I guess I don't have to tell any of you guys here, like the first time automation was first implemented was 1986 when Pfizer, I believe so, but you guys might know better. But Pfizer began using physical automation to increase the rate of biomolecule screening for the identification of pharmaceutical candidates. And like since then, they're like, oh, automation of science is just around the corner, is just around the corner. But what might make this time different? And so, I mean, one thing is that physical automation is kind of more accessible now. Uh, but I think the big thing, and we all know, is that co the player in the elephant in the room is cognitive automation and kind of advances in IT and computational methods. And so cognitive automation makes physical automation more valuable through synergy, increasing the value of large data sets, increase the speed by which data generated from physical automation can be processed, increases the ability to extract value from high throughput techniques, including generating insights from null data or like carrying that over. Um, and then obviously the hype around closed loop systems. Um, I say that very lightly because I mean it's really cool. Um, but yeah. And then makes automation engineers easier and empowers automation literate scientists to get more out of automation. And so I'm saying automation a lot, sorry. And that's primarily driven by LLMs, whether some think LLMs are the bee's knees or overhyped is another story. But and so using LLMs to generate things like protocols and using MCPs between LLMs and platforms to be able to communicate with hardware. And so what? So why is that so great? Why do we care? And so the hope is that the ability to efficiently produce and process vast amounts of multidimensional, multimodal data will be used to identify meaningful patterns and create models of systems that encapsulates more complex relationships. We know biology is really complex, and the idea is that by using advanced automation, you can uh, more easily, more efficiently, and more intelligently kind of navigate that space. And so the idea is that this will lead to greater speed and efficiency of biotech innovation, advancing our understanding of biological systems, and facilitate the development of personalized medicines and biomanufactured consumer goods. And those are just examples. And so what did I do here? Going well in. I interviewed about 14 senior decision makers across 10 companies, biomanufacturing, drug discovery and pharmaceuticals, contract research and development providers, and I also spoke to an additional, I think like four automation engineers. Could be a little less, could be a little more, but I think it is about four. Um, Let's see. How am I doing? Okay, I'm gonna try and I'm probably gonna speed through these first two sections, but I did find them interesting. I did make slides for them. So this is this first section, which is a little bit more on workforce and also geared towards kind of these not yet automated labs. And so there's organizational value, operational, and workforce impacts. And so the first section 1.1 is organizational value. And just broadly, I'm just going to broadly touch on these. And, if you have more comments, you can always reach out to me if you're like, hey, this stood out, this didn't make sense, or this did make sense. You can always reach out. My email's on the side. But I found that implementing advanced automation increased organizational bandwidth, freeing the organization to kind of offer services or products faster. So get a leg up on the competition, be able to, turn around projects quicker, pursue a greater number of projects. So be able to say, hey, we've had project X. Now we have the bandwidth to do project Y and project Z. We don't have to just focus on Project X. And one company even started up an alternative business model with the bandwidth that advanced automation afforded them. However, this impact is largely still limited to the R&D process. And is only just starting to proliferate into kind of like biomanufacturing, like the kind of actual manufacturing, actual industrial side, um, not including pharma, of course. Pharma's a different case, where it's a little different. Then my second part of this is the operational and workforce impacts. So I found that automation supplanted medium skill tasks and processes. So things that are done in a high enough throughput, but isn't novel, and also isn't something very basic. So things like plasmid genotyping. And so I'll kind of go a little bit more into what medium skill is, but this led to a shift in employee task diet to higher value tasks such as planning and designing experiments, exploring orthogonal methods, analyzing and synthesizing results. And so that actually resulted in these companies reportedly having an increased proportion of workers with higher degree of education and potentially skills. They specifically called out education, but yeah. And so this actually kind of aligns with the literature of the impacts of automation generally and the general trends in jobs since the early 90s, maybe even the 80s. And so that kind of complexity, on the x-axis, we have task complexity within a job, while, sorry, hopefully that's not very loud. My clock got reset. Um, and on the y-axis, worker skills. And so here it's basically showing that capital or automation will replace kind of the middle skill work, while these like, Gabby, stop. Um, while labor will still be executing these like low skill tasks, things like moving plates around or refilling reagents or reshelving reagents. And then these kind of higher end tasks, which I said, planning experience and whatnot. Um, yeah. So as I kind of said, task of intermediate complexity take over by capital, while tasks at the extremes are performed by workers. And then kind of here what we see is that once the productivity of machines increases, you have these higher skill workers needing to have even higher skills, and the lower skill workers need, you just need them for even lower skill. Yeah, even lower skill tasks. But the one question was like, I said that these organizations said they had a higher proportion of high skilled labor. So, like, where did these lower kind of tasks go? Um, and that's in kind of, it was interesting because I found this paper, this digitalization paradox of everyday scientific labor, where they went into academic automated labs in the UK, and they found that yes, automation helped with a lot of medium skilled tasks, but scientists were then also tasked with a lot more mundane work, low skilled work. As I kind of like mentioned before, like, troubleshooting the machines, figuring out how to get them to work, like um, things of that nature. So mundane knowledge work is amplified and diversified in the biosciences, and that's something that like I didn't hear about. I don't know whether it's like um, those tasks just get distributed to the high-end labor, and like, so there's actually, they get two additional things on their plate. Just the companies I talked to didn't mention that other plate, or whether maybe, you know, um, companies have, I don't know, companies were just not reporting like these lower skill labor, or whether LLMs and AI kind of help reduce the need for or the instance of these type of skills. But yeah, I thought that was worth mentioning. Um, and so I kind of see that this leading to two types of companies in the future, which I kind of saw. On one side, we have like service-based. And so I saw this with like cloud labs, where a majority of the workers are going to be low skilled, supported by an okay amount or a solid amount of high skilled labor and even in a very low amount of medium skilled labor. On the other side, we have like R&D driven companies that may have a higher proportion of high skilled labor, and that's driving a majority of their work with a moderate amount of low skilled labor to kind of pick up those easy tasks and an even lower amount of medium skilled labor. Uh, And so my recommendations for this is for targeted towards biotech firms. And so that is like to increase the rate of value generating activities. Biotech companies investing in R&D should assess their own processes and workflows to identify opportunities to integrate advanced automation, considering value in terms of increased bandwidth and efficient deployment in capital. And essentially, like what I say in the paper is that when there's these workforce shifts happening within a company, like you need to be attentive that people don't lose interest in their jobs. And so you'll have to probably be shifting around workforce responsibilities. And companies should try and make sure that people in their positions have opportunities to build agency. Yeah, essentially so people can feel connected and feel valuable in what they do. And my second recommendation is to maximize employee productivity and organizational outcomes. Kind of what I just said. Companies integrating advanced automation into their workforce should develop a plan for adapting to changes in the distribution of labor needs. So that's part one. Time check. Okay. Yeah, okay. Um, So part two is facilitating successful integration on the company level. And so the idea here is that what do you need to know before kind of just buying something um, in order to be able to kind of ensure success, right from the get-go, but also sustaining that success in the long term. I mean, I bet we all know, I heard countless examples of instances where equipment just gets kind of abandoned, something doesn't become relevant anymore, and maybe a big investment kind of ends up going sour. Um, and so once again, I'm going to briefly go over these. Yeah, very briefly, but if anything stands out, you guys can let me know. You can interrupt me. We can talk about it at the end. You can email me, but and so it's the first kind of part of this section is I came up with these five principles. Some of them are very basic, some of them are a little bit more complex. But the first one is robust science underlies success. Automation cannot remedy fundamental scientific issues or ensure success on its own. You can't just buy a solution and be like, now my company is gonna be able to be number one or like this assay isn't sensitive enough if I just had automation. um Sorry, the next two came up. The second is advanced automation become requires a long-term outlook with careful planning and a strategy. A lot of the times you won't see kind of financial payoff, but there are a lot of kind of other strategic benefits, or you just got to, think about in the long term. So, yeah. Um, Number three is the ability to increase throughput brings new challenges. And so I talk a little bit about needing to build automation literacy and efficiently translating, bench from the bench to the machine. So automation can increase throughput, but reduces flexibility. That is a core proposition of automation. Data infrastructure serves as a foundation of advanced automation. If you don't have good data infrastructure, if you don't get good IT processes, it's all gonna be kind of not go very well. I think everyone has heard of the building data lakes and not data swamps analogy. So a strong fundamental infrastructure underlies success. And finally, long-term viability requires building an automation-oriented workforce. So advanced automation requires cross-disciplinary talent and teamwork, the cultivation or hiring, and needs the cultivation or hiring of automation literate talent. Um, and so whether that's investing in someone who's interested, and kind of getting them upskilled, and continuously having that person to be able to leverage the systems that you have, or it's getting an automation engineer or a data engineer in. Yes. Um, And so, like, from here, I kind of put together an example of an automation integration cycle. It's just kind of like an illustrative example. I think, anyone can kind of come up with one, and that might work better or worse for them. Um, and the idea being here is trying to drive home this like virtuous cycle of advanced automation whereby, getting some liquid handlers, getting some physical automation. You'll have a bunch of data. So, implementing cognitive automation makes managing and extracting insights from that easier. And therefore, you're like, okay, I want more data. And so you implement more automation. And then that demands, hey, I need more data infrastructure. I need more tools to analyze that to make it worth it. Okay, then let's get that. Okay, now I'm hungry for even more. And so I'm trying to put that here where, start with identifying robust, standardized bottlenecks within a workflow. Like it doesn't have to be standardized already, but standardizable. Assess the value and feasibility of advanced automation based on kind of some of the principles I had. Ensure enabling infrastructure is present, develop or acquire solutions, cultivate or acquire talent, introduce supporting automation for data management, and then iterate and sustain with where I put a big emphasis on this iteration that and why you need that talent to be able to adapt the systems for the evolving needs of your company. And so from here, it's just a pretty general kind of recommendation to ensure successful, sustainable adoption of advanced automation. Companies must develop roadmaps centered around capital, people, and their strategy. And so finally, I guess I saved the best for last, and this is this section that I'm talking about trying to get government to partner with the ecosystem to be able to support the proliferation of advanced automation and overcome challenges within kind of the ecosystem. And so here, so before I was kind of speaking pretty generally. It might have. I probably should have said that before. It might have made you feel weird, but I was trying to like talk about both cognitive and physical automation and the integration, the point of integration. But here I'm largely talking, I am going to be just talking kind of about the physical automation ecosystem. Because maybe I didn't talk enough people, but currently in the cognitive automation space, like it seems pretty good. Like they have a kind of pretty open culture, and the your coding and yeah, sorry. There's like standardized coding kind of languages, and um, haven't seen kind of big challenges in that space. But in the physical automation space, it seems like there are a lot more challenges. And so I kind of dug in more into that. And so that's why I'm bringing them out here. And
Can
so
I
the
ask you a question?
underlying, yeah.
Um, I mean, maybe you're about to get into it, but you're talking a lot about sort of, iterative and cyclical approaches. And then I think also on the cognitive automation, the way that culture can work differently. I wonder, anywhere in your conversations about this, was there any discussion about, I guess what I would just call low cost automation, ways to reduce the risk so that that iterative approach that you're talking about is more possible, or is that just not even on the table for most of the kinds of people you're talking to?
Yeah, yeah. Yes, so I've seen kind of uh that starting to maybe upswell. Well, I don't know if I want to say swell, but I know at least one person out of Duke is trying to, and I know that Tim, you and people around you have been trying this like low cost automation. But majority of that is like happening in the academic space. And trying to get the ball rolling on that and trying to get where trainees can get some experience, which is like I think, and in this section, some of the potential recommendations start to try and get at that. It's like there's this huge gap between like what you're doing in academia, both for engineers and for scientists, and like what you need to know going into industry. And so I think that efforts like that, like getting like low cost automation into the hands of students, is really important for that. But I think the people that I kind of spoke to were largely, I kind of try to move past the academic space and in the biotech space. And so there's a lot, yeah, less room for like, trying low cost solutions and seeing how things go, which seems kind of odd because yeah, it seems like pretty much like they go big or go home, and if it works, it works. And that's the thing, like there's a survivorship bias in terms of who I spoke to. Like these are successful places. Um, uh, and then the ones that I ran into that weren't successful were either like Stratios and it got bought out, or it's these academic places that just like stopped using it, stopped like usually didn't have someone hired to be able to like sustain the system, and so it like went away. But I think Lewis had his hand up.
Yeah, I think one of the things that I love about the low cost automation stuff is that my hope is that it provides a blueprint for the future. But one thing I will add here is that oftentimes in industry, the timelines are so tight that you don't have that development life cycle. And then secondly, these are people's jobs and their careers. And I've definitely seen directors and VPs and managers get fired because they made a decision that ended up costing more in terms of resources. So I think there's an incentivized aversion to risk because of just this lack of like cognitive automation and leadership period. And so like if you sort of say, hey, yeah, we're doing this low cost automation solution, it's going to scale, but it's going to take 1, 2 years to really develop further along. That's just a huge, huge risk. And I think that if you're building a clinical diagnostics or some sort of like drug product pipeline on that, there's less appetite. So I think those are all considerations. But I have definitely seen people get absolutely lose their jobs because they made the wrong investment, just as a heads up.
Definitely. Thank you, Lewis, and Andy.
I wanted to just build on what Tim, I think, was asking by bringing like openness into the discussion. I'm curious what your thoughts are and what the opinions of the people you talk to are. I'll say that in my limited experience, I find it fascinating that people find openness to be scary. And because I think it culturally runs against a lot of the like normal tendencies in like for privacy and secrecy and total control within these environments. But I also am frequently evangelizing to people that this is a huge opportunity for robustness and to create systems where you're not dependent on exclusive distributors and that kind of stuff. And I'm just curious what your thoughts are and what conversations you've had with people.
Yeah, definitely. I think, uh, I mean, what really stands out is actually a recent conversation with Madeline Wolf here. I think she's like the expert on this. She kind of developed her website and blog posts about this. And one of the kind of big things, and so I'll kind of repeat what I've heard from her, but then add my own little piece after that, uh, is that like it seems like the culture is changing. Like, especially with like the younger automation engineers, like they're not happy with just buying like a solution out of the box and then just using it for how the manufacturer imagines that the user would use it. Like, that's kind of the biggest driving thing towards this like open and standardized methods is that like you want to be able to plug in different tools and get them to work and get them like upstarted and not have to like spend months on getting things to work. It's about like buying a solution and not having to worry that the company will uh, go out of business and they use some weird programming language and like you don't know how to figure, you can't figure it out. Like, or like the kind of operational protocol manuals like just disappear. And I think I'm gonna like contrast this. I think it's very realistic to have it happen just because it benefits it kind of benefits everyone except maybe the tool developers. Like I think those are kind of the biggest friction point because unlike like well, I'm just going to bring up like biomanufacturing on the other hand, where there's a drive to try and share data on scaling failures. But businesses are very like kind of against that because they're like, oh, what if it like shares our business secrets? But it doesn't feel like, and maybe someone can correct me if I'm wrong, but that sharing how to get your lab automation like up and running, up and like connected and like troubleshooting it and liquid classes and whatnot, like those aren't kind of uh related to products and potentially like trade secrets around the actual products that are being produced. Like this is about getting the tools to work. But if anyone wants to add to that, I will go ahead.
I'm gonna time check you. I think we've sort of dragged you into a really interesting conversation, but we're at 9:17, so got about 13 minutes left.
Yeah, I'll try and be kind of quick to continue um, with discussion as well. So, I guess I already went to my next slide. I will skip the, yeah, underlying thesis was that there's things that hither the broad adoption. That like broad adoption is not about like people not wanting it. It's also about like there's challenges to getting things going, and and that's why people aren't using it. And like, yeah. And so my other thesis is that my recommendations will help clear these barriers. Um, and so the big one is kind of standard operating system. I'm not going to go into depth, but the idea is that it makes training automation engineers more difficult, makes hiring them more difficult, makes moving between jobs for automation engineers more difficult. Oh, one question that maybe someone answer in chat, but um, maybe this also increases fragility, harder to service, more prone to errors when you're just like freewheeling, I don't know, using LMs, using your own solutions to get things connected and working. Like there's just shit just doesn't work. But I didn't necessarily hear this. I was calling it out. I was like, it seems like it. Um, I feel pretty confident in this next recommendation, but to kind of try and remedy that, and that is to set the stage for thriving advanced automation ecosystems, hoping that National Institutes for Standards and Technology should coalesce the physical automation community to advance the widespread adoption of a software hardware communication standard within the next 2 years. And I'm thinking that this would enhance usability, accelerate development, improves the sustainability by fostering more robust, trainable workforce, and also get like systems. Engineers can build systems quicker, can retool them for evolving needs of their business. In 3.2, this one, I'll do my things first. I'm not sure how I feel about this, but there's this whole part about human machine interface. Sometimes you don't have automation engineers, but it seems like the UX UI environments are kind of that providers kind of provide are too usually too limited for automation engineers and insufficient or too clunky for experimentalists or both. The one thing is that, user experience is important is critical for converting users. And so I don't know how I feel about this, but how much value this would provide in terms of the investment. But to set the stage for a thriving advanced automation ecosystem, maybe the SLAS should convene the physical automation community to advance the widespread adoption. Oh, sorry, I didn't update this. Sorry. So I was thinking that like some set of basic UX UI design principles, some like kind of standards around UX UI to like serve as a resource for those kind of developing user interfaces to be able to use. Yeah, just so that there's a kind of more robust user interface and user experience across the ecosystem to kind of help with those adopting. And I think this one is more specific towards that non-automation people touch point. Yeah, sorry about the non-updating of the recommendation. And the third kind of big one, wait, sorry, let me see. Okay, no, sorry. The third one I have is the ecosystem would benefit from a centralized resource center. So automation engineers currently spend countless hours repeating instrument standardization, recreating protocols, and solving common problems. Like Stack Overflow for coding, automation engineers need a culture of and a place for these recipes and sharing them. Um, I feel pretty good about this one. And so that is to accelerate the ability of advanced automation to promote bioinnovation. I'm thinking the National Institutes of Health, I mean, sorry, National Institutes of Standards and Technology should support SLAS. Um, there might be more kind of other places that people might feel strongly against SLAS, but in the development of a resource hub to host information on standard protocols for physical lab automation. And I think like getting something up started, should be quick, but I think the buy-in is the difficult task. Um, and then the last one, whoops, okay. Um, Sorry, I didn't do an introduction for this last one. So the last one is the one that I was like trying to facilitate, like what would be the most useful at this stage, at this maturity of physical automation, and that is like, how do we get more people to be automation literate? And that's like, how do we get engineers to be interested in lab automation? And how do we get scientists to be able to at least like know how to figure out how to use one and know how to kind of and have like some sort of sense of what it means to translate a bench experiment um, to um, to a lab automation device, yeah, lab automation system. Um, oh man, I lost my time. Um, and so some of the things I was thinking about is like whether we start on this community side and like there needs to be more initiatives on like community programming to informally upskill and things like Lewis and like try and scale that type of activity, but upskill scientists and engineers to with skills in advanced automation over the next 2 to 4 years. Should it be something like NSF, NIH, and the Department of Labor, and in partnership with industry, create more opportunities for undergraduates and graduate students to go into places that have laboratory automation and do like short-term internships. In biology, we don't really do like co-ops and internships like that often. It's usually just going to the lab at your university. But maybe we should scale the ability for scientists and engineers to get more experience with lab automation, kind of informally, outside of their education programs. And the biggest one is like get DOE, NIH, NSF to begin an interagency collaboration to establish regional shared advanced automation systems operational within the next 2 to 6 years. And the kind of driving ethos behind that one is to actually get automation in the hands of biological scientists and engineers, and giving opportunities for early career individuals to use these systems and provide them with industry relevant skills to reduce the gap between uh, academia and industry. And so the idea there's similar things in the kind of chip industry where there's like free to use by academic users, and for industry users it would be kind of a pay to use model. And yeah, that's what I have. Sorry about going through that last part a bit, but we have 5 minutes. If anything caught anyone's ear, we can kind of discuss that further.
Hey, all right. Let's give Jonathan a round of applause. Get some emojis going. Uh, cool. I'll stop the recording there, and then we can have a little conversation in these last few minutes.